Hello friends, today we will have a detailed discussion on the mechanism of unimolecular elimination reactions. So we will start with an example of an alkyl halide. So let us see this alkyl halide. This is our tertiary butyl iodide. So this is reacting with a base H2O. So we will be getting a alkene here. So this alkene is formed plus H3O plus plus I minus. So this is a reaction. This is proceeding by the even mechanism here. That is tertiary butyl iodide reacting with a base H2O giving an alkene here. Correct. So this is many characteristics of the even mechanism. It is similar to the SN1 mechanism. That is the substitution unimolecular substitution reactions, SN1 reactions. Many characteristics are identical, similar. Here, the kinetics, if you see the kinetics, this is the first order kinetics here. Now, the rate of the reaction, it is dependent only on the, rate. It depends only on the concentration of the alkyl halide here. Okay, so the rate of the reaction is independent of the concentration of the base here. First order kinetics, the first step is the slow step. Now, the reaction proceeds in two steps. We can say the first step, as in the case of the SN1 reaction, that is the bond to the leaving group that is broken first. That is the heterolytic cleavage of the CX bond here. So, CX bond, here in this case, is the CI bond. That is the heterolytic cleavage of the CX bond. That is the first step here. Okay. So, a two-step mechanism. The first step is the heterolytic cleavage of the CI bond. It forms an intermediate, a carbocation intermediate here. Okay, the bond to the leaving group, it is broken first and before the pi bond it is formed. So, let us see the step 1 of the reaction, how it looks like. So, I will just clear this page. So, step 1, we can say it will be, so this is our alkyl halide here, tertiary butyl iodide. Okay, so this is our leaving group here, I. So the leaving group goes along with the electron pair. Correct. Now it will be the slow step here. Slow step, that is the rate determining step here. So we will be getting a reactive intermediate, that is the carbocation here. Okay, this is the first step of the reaction. A carbocation is formed, that is the CI bond. Here the CI bond, it is heterolytically cleaved. That is the heterolytic cleavage of the CI bond here. Okay. Now, in the second step, what happens here? This carbocation, that is the CH bond, that is cleavage of the CH bond. That is the beta CH bond here. That is, this is step 1. Now, the step 2 will be the carbocation okay, so this is our beta hydrogen here, CH bond here, beta carbon. Okay, beta carbon means the carbon adjacent to the positively charged carbon here. Okay, so the CH bond, it is cleaved and the pi bond is formed. So the reaction will be, say first what happens here. So we have this base H2O here. H2O is here. So this will be reacting with this proton. Okay, the base removes this proton here and a pi bond will be formed. That is, pi bond will be formed in this fashion here. Correct? So this is the step 2 of the reaction here. That is the CH bond, it is cleaved and the pi bond is formed here. The CH bond means the base removes the proton from the carbon. It is adjacent to the beta carbon. That is that is called a beta carbon. That is the base. It is removing the proton from a carbon adjacent to the carbocation. That is the beta carbon here. Okay. Now the electron pair in the CH bond. So it is used to form the new pi bond. So this will be giving a alkene here. This alkene is formed along with S3O plus. Okay, so this is the even mechanism here. That is, two steps are there. The first step is the slow step, rate determining step. So the cleavage of the Ci bond, that is the CX bond, that is heterolitical cleavage, and we will be getting a positively charged, the electrophilic center, that is the carbocation is formed here. And in the step 2 of the reaction, the base removes the beta hydrogen here. That is from the CH bond, beta carbon. Base removes a proton from a carbon adjacent to the carbocation here. Now, what is the essential difference between this, the E1 and E2 mechanism here? In the both cases, the number of bonds broken and the number of new bonds formed, they are all same thing. There is no difference here. Okay, now the difference is only in the timing. That is the timing of the bond cleavage, bond breaking, and the formation of the new bond here. So in the even mechanism, the leaving group, okay, it comes off before the beta proton is removed here. Okay, and the reaction occurs in 2 steps. So in the E1 mechanism, so E1 and E2, so E1, the leaving groups comes off first, and we get a carbocation intermediate here. Okay, and subsequent reaction, subsequent step of the reaction, the beta proton is removed. But in the case of E2 mechanism, okay, it is a single step mechanism. That is, only one step is involved here. The leaving group comes off simultaneously as the beta proton is removed. That is both the activities, that is the removal of the beta proton and the coming of the leaving group. Both the things take place simultaneously. Okay, this is the difference between E1 and E2 mechanisms here. Just like in the case of SN1, we can draw an energy diagram and all this kind of a thing. Here also we can do that, but I will not be going into that now. So we will be discussing mostly the characteristics of the even reactions here. What are the main characteristics of the even reactions? That even mechanism, we can say the rate of the even reaction here. It will increase as the number of R groups, that is the substituent alkyl groups on the carbon atom with the leaving group, increases. That is the first point which we have to see. So let us see the rate of the reaction, how it will be. So the rate of the reaction here, what will be the order of the rate of the reaction? So now we have seen that we have this primary RCH2X. This is the primary alkyl halide. Then we have R2CHX. This is the secondary alkyl halide. Then we have R3CX. This is the tertiary alkyl halide here. That is, the number of alkyl groups on the carbon atom with the leaving group keeps on increasing here. Now, as the number of the R groups, alkyl substituents on the carbon with the leaving group increases, the rate of the even reaction increases. So the order of the rate of the reaction will be like this. From left to right, like this, we can say this is the order of the reaction, increasing rate of even reaction. Okay, so increasing rate of even reaction, that is, as the number of alkyl substituents increases, the rate of the even reaction increases. That is the first point here. Now again, the carbocation stability, we can say this is the primary carbocation RCH2 plus. So this is the primary carbocation. Then we have R2 say CH secondary. Then we have R3C plus. This is a tertiary carbocation. Now the stability of the carbocation increases from left to right here. That is, the tertiary carbocation, it is the most stable compared to the secondary and compared to the primary one. So the primary carbocation, it is the least stable carbocation here. Therefore, increasing carbocation stability. So this is the order of increasing carbocation stability. So as the carbocation stability increases, the rate of the even reaction increases. As the number of alkyl groups increases, the rate of the even reaction increases. And in the same way, as the stability of the carbocation increases, the rate of the even reaction increases. Okay, this is the order here. So increasing alkyl substitution, it has the same effect in the case of E1 and E2. Okay, that is same effect on the rate of the even reaction and the E2 reaction here. E2 mechanism and E1 mechanism. So the order will be like this, we can say, that is, I'll just, so RCH2X, it will be less order of the rate of the reaction here, then R2, then we have R3CX here. Okay, tertiary one. That is the order of the reaction here. Correct. That means in the case of E1 and E2 reactions, increasing alkyl substitution, it has the same effect here. Okay, increasing alkyl substitution increases the carbocation stability and the reaction of the even reactions rate, it increases here. Okay, now another point, important point which you have to note here, in the rate equation, that is, rate depends upon only the concentration of the alkyl halide. The base does not appear in the rate equation. Therefore, weak bases, it will favor even reactions. Weak bases favor even reactions here. Okay, the strength of the base, it determines whether the reaction will follow the even mechanism or the E2 mechanism. So the deciding factor, it is the strength of the base. That is most important point here. The strength of the base, it will determine whether the reaction proceeds by the even mechanism or E2 mechanism here. Now, strong bases. Let us see another example here. Strong bases. That is, in the case of even mechanism, so we have seen, because the concentration of the base, it does not appear in the rate equation, the weak bases, it will favor even reaction. Even reaction means weak bases. Weak bases will favor even reactions. Okay, that is, weak bases, like say, we can say neutral bases like H2O, then ROH, all these kind of a thing will favor even reactions here. And strong bases, so strong bases, that is negatively charged bases like say OH minus, then we have OR minus, etc. It will favor E2 reactions. These are important points here. That is the base, concentration of the base here. Okay, the strength of the base determines whether the mechanism is even or E2 here. Okay, strong bases, OH minus, OR minus, it will favor E2 reactions. Weak bases, neutral bases, H2O, ROH. Okay, it will favor even reactions here. Okay, now we can say even reactions are, another important point here, they are regioselective reactions. Okay, now even reactions are regioselective in the sense, what is regioselective? We have seen here earlier, regioselective reactions. That is, we have discussed that Zaitsev rule here. This rule, actually as per this rule, when alkyl halide containing or having different beta carbon atoms. Okay, different types of beta carbon atoms means we get a mixture of alkenes here. Okay, that is, different constitutional isomers are possible. Then the more stable constitutional isomer or the alkene, it will be the one with the maximum substitution. That is the more substituted double bond. Alkene with the more substituted double bond, that means the alkene, the more stable alkene, that will be the predominant product or the exclusive product, we can say. That is the Zaitsev rule here. So that is what is meant by regioselective. Even reactions are regioselective. It will favor the formation of the more substituted and more stable alkenes. Correct? More substituted and more stable alkenes here. Correct? That is one point, regioselective one. Then the another one is the polar protic solvents. So even reaction, it will be favored by polar protic solvents. How? Because that will solvate the ionic intermediate. Okay, that is the polar protic solvents that solvate ionic intermediates, the carbocation and all. Okay, so that will be favoring the even reactions here. Now let us see an example. So even elimination. One example I will just show you, so that it will be clear to you. Say a compound of this nature. Let us see. So cyclopentane here. So cyclopentane, say one methyl group, one methyl. Then we can add one, say, bromine. We can add here. So that means one methyl. We can say one bromo, one methyl cyclopentane. Now even elimination of HBr from this one. That is elimination of HBr. Say with a base, say H2O. We can say H2O. H2O is the base here. Correct. Now here, what are the different types of beta carbons here? So these two carbons here, this is one carbon here, this is a beta 1, I can say. So this is another beta carbon, this is another beta 1. That is, these two carbons are identical carbons. Therefore, beta 1 only. I am just noting it down. Now the CH3 carbon here. So this is a different type of carbon. So this will be a beta 2 carbon here. That is, two different types of beta carbons are available. Therefore, we will be getting a mixture of alkenes, and it will be followed by the save rule here. Correct. The most substituted alkene, it will be predominant or exclusive product, the major product we can say. So two alkenes will be formed here. What will be the nature of these alkenes? Let us see. One alkene will be, this is the most substituted alkene here. That is, this is a tri-substituted alkene. So the tri-substituted alkene, it is the major product. Okay. Now another alkene will be formed here. This is another alkene. Possibility is there. This is a di-substituted one. Correct. This is a di-substituted alkene. So this alkene, it will be a minor product. Okay, this will be a minor product here. So different types of alkenes are possible here. That is the regioselective reactions here. Okay, regioselective reactions here. Now in the case of SN1, now let us have a comparison of this SN1 and even reaction here. So both have the same first step mechanism. That is, in the case of, say, SN1, we have SN1, then even reactions. Okay, these two things, both these reactions, they have the first step is the same thing, which we have seen, a formation of a carbocation intermediate here. So we can say something like this here, say CH. So this is the carbocation I am just drawing here. Okay, this is the carbocation. So then the difference, what is the difference here? SN1 even and even reaction, the first step is the formation of the carbocation. It is the same thing. So the difference is only in the subsequent step. So what happens to this carbocation subsequently? That is more important here. So in the case of an SN1 reaction, so the nucleophile here, negatively charged nucleophile, so it will be attacking this electrophilic center. Okay, then we will be getting the product here. A substitution product will be formed here. This is the product. This is a nucleophilic substitution. See, the nucleophile attacks the electrophilic carbon atom here. So in the case of elimination, that is even, what happens here? The base removes that proton here. Okay, so we can so here we have this proton here. This proton will be removed by this base. This is the thing. So this is the carbocation here. So then no, positive charge will be on the adjacent carbon. This is the carbocation here. Okay. So this is the type of reaction. Now here the CH bond, the electron pair in the CH bond, it is used to form the pi bond. The new pi bond is formed in the case of E1 mechanism here. So this is the difference here. E1, the base attacks the beta proton here. Okay, then we will be getting this alkene here. That is a new pi bond, it is formed. The intermediate is the same thing, but a new pi bond, it is formed here. Now, the thing is the same conditions that favor the substitution by an SN1 mechanism also favor elimination by an E1 mechanism. That is, the conditions are the same thing here. Okay, that is the condition which favor an SN1, that is a substitution reaction, and the conditions that favor an E1 reaction. Okay, these conditions are all similar, same conditions. Then what happens? As a result, both these reactions will take place simultaneously. When E1 reaction is taking place, there will be a competing SN1 reaction. Therefore, we get a mixture of products. That is the biggest drawback here. In the case of an E1 reaction, we don't get a pure product because there will be a competing substitution reaction because the conditions are same. That is the conditions favoring E1, conditions favoring SN1. Both are same thing. Therefore, these two reactions take place simultaneously. There will be a competing SN1 reaction. When you are expecting an elimination reaction, there will be a competing SN1 reaction there. Therefore, there will be a mixture of products formed. Okay, both reactions usually occur in the same reaction mixture. Therefore, a mixture of products will be obtained there. That is the biggest drawback here in the case of E1 reaction. So, E1 reactions often it occur with a competing SN1 mechanism, SN1 reaction of alkyl halides. Therefore, E1 reactions of alkyl halides, they are of not much use. They are not very useful. E1 reactions not very useful because we don't get a pure product, not very useful. Because we get a mixture of products there. Okay, that is the reason here. So E2 reactions are more common reactions and useful reactions here. Now I will just show you how this SN1 and E1 reactions are competing SN1 and E1 reactions. We can say when we are expecting E1, there will be a competing SN1. Therefore, we'll be getting a mixture of products here. So let us analyze how it is possible. Just an example. I can just suggest to you. I can illustrate this thing with a small example. Again, we can say that a tertiary, say butyl bromide or butyl iodide or whatever it is there, we can just take it here. Okay, so that will show you how this reaction is proceeding. So if you are having a compound of this nature here, so CH3, this is the compound we have been seeing earlier. So this is say bromine, we can say iodine or bromine, whatever. So the first step, it will be the heterolytic cleavage of the CX bond here. Okay, this bromine, it will leave along with the electron pair, that is the leaving group here. So this is the slow step. Slow step is the rate determining step here. So we will be getting a carbocation intermediate. Okay, so this is the first step of the reaction here. Correct? Plus Br minus. Now, the second step of the reaction will be, say, let us see what will be the SN1 reaction. SN1 reaction means reaction of the carbocation with, say, we can say H2O. H2O will be acting as a nucleophile here. Okay, so here, in the case of an SN1 mechanism, we can say this carbocation, okay, this carbocation, it will be reacting with a nucleophile here. This is the nucleophile, we can say water, H2O. So there will be, this is the kind of reaction we'll be getting here. Carbocation reacting with a nucleophile. Water will be acting as a nucleophile here in the case of SN1 mechanism. So what is the kind of product being formed here? So we'll be getting a product of this nature here. So CH3. Then it will be forming a bond with the water here. OH, OH2 plus. Okay, there will be a plus charge here, 2 electrons here. So this will be again reacting with this nucleophile here, H2O. So this proton it will be removed. That is a proton transfer reaction will take place here. Okay, so this electron will be shifted, displacement of this thing. So we'll be getting, say this reaction is known as a proton transfer reaction. So what will be the final product? Final product, it will be a neutral product here. Okay, there will not be any charge. So we will be getting an alcohol here. OH group will be introduced. So the nucleophilic substitution reactions are very, very useful for introduction of functional groups in the molecule here. Okay, so plus H3O plus. Okay. So this is the reaction here in the case of SN1, substitution reaction of the alkyl halide here. The first step, it will be the slow step, rate determining step. So the carbocation intermediate is formed here. So in the second step, the carbocation, it is reacting with the nucleophile H2O here, and we will be getting a positively charged intermediate here that will be reacting further with the nucleophile. Proton transfer reaction take place, and we will be getting an alcohol ultimately. Okay, that's a neutral product. Now, this is the case of SN1. Now, in the case of this is CH3 only. Okay, now even reaction. What will be the nature of even reaction? The carbocation, it is the same thing here. So instead of this SN1, the substitution reaction here, we will be getting the beta proton. The removal of the beta proton by H2O. H2O will act as a base here. In the case of elimination reaction, H2O acting as a base. SN1, it is acting as the nucleophile. There is a slight difference between these two things we have seen, we have discussed it earlier. Now, so let us see how is the reaction. Now, this carbocation, H2O acts as the base to remove the beta proton here. Okay, now CH3. So this is our carbocation here. I am just writing it again here. Then a positive charge. Then CH2. Yes, CH3, we write it like this here. Now, this is reacting with the base here, H2O. So this is the base here. So this will be attacking, taking this proton. Removal of this proton by this base here. Then this CH bond electron pair, it will form the pi bond. This is the elimination reaction here. Okay, we will be getting an alkene here. CH3, say double bond CH2. So this alkene plus H3O plus. So these are the two types of products. Two different types of products are formed here. In the case of an SN1 and even reaction here. When we are conducting the even reaction, there will be an SN1 reaction also. The first step, heterolytic cleavage. Okay, now the carbocation, it is reacting in this fashion here. The water, it will be acting, in the case of even reaction, it is acting as the base here to remove the proton here. The beta proton, it is removed. And we are getting an alkene as a main product here. Okay. So this is the alkene. So because of this reason, these even reactions are not of much useful to us in organic synthesis and all. Okay. Now this nucleophilic substitution, comparison between a nucleophilic substitution. Now we have seen that SN1 reaction and even reaction. Now generally there is a difference between the nucleophilic comparison between the nucleophilic substitution and beta elimination. Let us see now. So nucleophilic substitution means, say a compound of this nature, say C, then we can say X, correct? So this will be reacting with a nucleophile here. This is our nucleophile. So this will be, this is the leaving group here. This is the nucleophilic substitution reaction. So we will be getting C plus X minus. Okay, so this is the substitution reaction here. Okay, now in the case of beta elimination, how is the beta elimination taking place here? The beta hydrogen, it is removed here. So we have see a base, this remove this beta hydrogen here. Okay, so then this CH bond electron pair, it is forming the pi bond. So we will be getting an alkene here, like this an alkene will be formed. Then we will be getting say HB plus etc. and all these kind of thing, you see, plus X minus and all. Okay, so these are the products being formed here. Therefore, in the case of then this CX, it has to go, X has to go here. Okay, the beta elimination, that is the base attacks the proton, beta proton here, and X is leaving with the electron pair here. The CH bond electron pair, it is actually forming the new pi bond. So in both the reactions here, alkyl halide, the RX, this is the alkyl halide here. Okay, this alkyl halide, it acts as an electrophile here. Alkyl halide, it is acting as an electrophile. Okay, so reacting with an electron-rich reagent here. So both the reactions require a good leaving group here, because the leaving group should go along with the electron density in the CX bond here, because a better leaving group or a good leaving group, that is more important here. Now here the difference here in the substitution reaction, a nucleophile, okay, so it attacks a single carbon atom here. Nucleophile attacks a single carbon atom. Here we can see this carbon atom is attacked by the nucleophile here. Okay, in elimination reaction, what happens? The base removes the beta proton here, okay, to form the pi bond, and therefore two carbon atoms are involved here. This is the only difference here in the reaction between the substitution and elimination reactions. Now we have seen this E1 and E2. Now let us see what is how will you compare. Briefly I will just explain to you the comparison of these two E1 and E2 mechanisms here. E1 reactions and E2 reactions. So E2 first I will write, then we can write E1. Okay, I will just explain to you what is the mechanism in the case of E2. So E2, it is a one-step mechanism, and E1, it is two steps. Okay, these are the basic difference here. E2, it is a single-step reaction. E1, it is a two-step reaction. Now, alkyl halide. In both the cases, we need an alkyl halide here. Now, the rate of the reaction we have seen. The rate, in both the cases, the rate will be, that is a tertiary alkyl halide. The reaction rate will be higher compared to secondary and then compared to primary. So RCH2 X. So this is the rate order. Okay, rate of the reaction in both the cases of E1 and E2, the rate depends upon the alkyl substitution. The more it is substituted, alkyl substitution is more, means the rate will be more here. R3CX, I have just shown the order here. This is the order of the reaction here in the case of alkyl halide. Now the rate here in the case of E2 reaction, the rate depends upon the concentration of the, say, rate is equal to, say, K into the concentration of the alkyl halide, okay, and the base. That is in the case of E2. This is for E2, correct? So in the case of E1 rate is equal to K into Rx, only the alkyl halide. This is the difference here. Essential difference between E2 and E1 mechanism here. The first thing is E2 is a single step, E1 is two steps. Alkyl halide, we can say the rate, it depends upon the alkyl substitution. More substituted means the rate is more, correct? Now, in the case of rate equation, if you see that, in the case of the E2 reaction, the rate of the reaction depends upon the concentrations of the alkyl halide and the base. Whereas in the case of E1 mechanism, the rate depends only on the concentration of the alkyl halide. So it is independent, the rate is independent of the concentration of the base in the case of a E1 mechanism here. Okay, now base. The next point here, it will be, say, we have discussed the base, the nature of the base here. Okay, so strong base and weak base here. E2 reaction favored by strong bases. Even reaction favored by weak bases. Okay, base, that is strong means strong base. It will be favoring the E2 reaction. Weak means it will be favoring even reaction. Okay, these are the differences which we have to note here. Okay, that is even mechanism or even reaction favored by weak bases and E2 reactions favored by strong bases. Correct. Now, leaving group. Leaving group, we know better leaving group. In both the cases, we need good leaving groups because the electron density in the CX bond, it is to be absorbed. Okay. Now, solvent is a very important point here. More important point is solvent here. That is, one is favored by polar protic solvent, other one is favored by polar aprotic solvent. That is, E2 reaction favored by polar aprotic solvent. Polar aprotic solvent. This is favoring the E2 reaction here. Okay, polar aprotic solvents favor E2 reaction, and protic solvents, it will favor even reactions here. Okay, so polar protic solvents will favor even reactions. Now the product, nature of product formed here, we have discussed that is a more substituted alkene. In both the cases, the Zaitsev rule, it will be followed. In both the cases, in the case of E2 reaction and even reaction, we will be getting the more substituted alkene. More substituted alkene will be formed in both the kind of reactions here. Okay, now you see, when is the mechanism E1 or E2? That is the important thing. Briefly, I will tell you. That is, we have you see a particular starting material. We have got a particular starting material and a base. Okay, now how do we know whether the reaction will proceed either by the even mechanism or by the E2 mechanism? Okay, now the identity of the alkyl halide, it is not that important here because we have seen the rate of the reaction. It will depends upon the more substituted and all we have seen now. Okay, the identity of the alkyl halide here, it is not that important to decide the course of the reaction. That is the mechanism of the reaction, to determine whether it follows, the reaction follows the even mechanism or the E2 mechanism. We cannot go by the identity of the alkyl halide. That is the substitution, alkyl substitution. Okay, that is what we mean by that. Okay, because the rate of the both the even and E2 reactions here, we have seen it increases as the number of alkyl groups, that is the R groups on the carbon with the leaving group. Okay, it increases. Therefore, in both the reactions, in even and E2 reactions, more alkyl substitution means the faster the reaction, the rate will be more. Therefore, the identity of that alkyl halide, it is not that important for us to determine the mechanism here. Now, the only thing is the strength of the base. That is the important point here. That is, the strength of the base is most important thing for us here. Strong base, weak base, strength of the base. Okay, this is the important point here. Strong bases favor E2 mechanism, we have seen. Weak bases form even mechanism. So that is the comparison here. Strong bases, that is negatively charged bases like OH minus, then OR minus and all this kind of a thing, So that will be favoring a E2 mechanism. Then weak bases like ROH, H2O, etc., it will be favoring even mechanism here. So this is the basic thing, fundamental thing which we can think of. Okay. So then another point we have discussed, that even mechanism and all less useful because a mixture of SN1 and even products are being formed and all this kind of a thing. Okay. Now, most important thing, another important thing which we can see, the E2 reaction, the application of the E2 reaction in the synthesis of alkynes. Alkyne synthesis. That is, using the alkynes are hydrocarbons having 2 pi bonds. That is a triple bond here. Hydrocarbons containing a triple bond, that is alkyne here. Okay, so first we get an alkyne, single elimination So single elimination means we will get an alkene. So this is the important thing, E2 and alkyne synthesis. So from an alkyl halide, a single elimination reaction, it produces only one pi bond. So one pi bond means it will be an alkene. An alkene means this is an alkene here. That is one pi bond. Alkene will be there. So what we want, alkyne. This is the alkyne. A triple bond here, alkyne. That is, this alkyne contains 2 pi bonds. Okay, 2 pi bonds. So for getting 2 pi bonds, we need 2 eliminations. Important point. 2 eliminations are needed here. A single elimination reaction, it will produce only 1 pi bond, so we will be getting only an alkene. Correct? Now 2 consecutive eliminations are needed here. 2 consecutive elimination reactions, it will produce 2 pi bonds here. Okay, and then we'll be getting an alkyne here. Okay, so alkynes are prepared by 2 successive dehydrohalogenation reactions. We have discussed this point, dehydrohalogenation reactions. So successive dehydrohalogenation reaction. 2 reactions are needed here. 2 elimination reactions are needed to produce an alkyne here. Okay. Now let us see, 2 elimination reactions are needed to remove 2 moles of HX. We will see that. So what will be the nature of the alkyl halide? We need a dihalide here. Because we have to remove 2 minus 2 HX, that is hydrogen halide, dehydrohalogenation reaction, 2 eliminations needed. Therefore 2 moles of HX are to be removed from the dihalide here. 2 elimination reactions are needed to remove 2 moles of HX from a dihalide. Now different types of dihalides can be used here. So what are the 2 different types of static materials here? So dihalide, that we can have a geminal and vicinal. What are they? 2 different types of dihalides we can visualize here. So one will be a vicinal dihalide. So vicinal dihalide will be like this, say R, say we can say H, then 1X here, then X here. That is dihalide. This is a dihalide here. Okay, this dihalide, it is a vicinal dihalide. Vicinal means what? That is, the halogen atoms are 2 X atoms are on adjacent carbon atoms there. Therefore, it is known as vicinal. VC. I'll write it clearly here. VC null dihalide. Okay, 2 X atoms on adjacent carbon atoms here. So this is a vicinal dihalide. Now another dihalide will be geminal, RCH. So we can, geminal means twins, 1X here. That is on the same carbon atoms. So geminal, this is known as geminal. Geminal dihalide. Geminal dihalide. Here the X atoms are on the same carbon atoms here. Okay, 2 X atoms on the same carbon atom. So geminal, it has come from the Latin word, I think. So Latin word geminus. Geminus. So it means twin. That is on the same carbon atom. We have got 2 halogen atoms here, X atoms here. Okay. Now these are the 2 types of dihalides which we are using for the synthesis of alkynes here. Now normally we need strong bases again, because we have to remove 2 moles of HX here, minus 2 HX. That is the difference here. Okay, strong bases are usually needed to synthesize alkynes by the dehydrohalogenation reactions here. Okay, the strong bases are usually needed for the synthesis of alkynes by dehydrohalogenation reactions here. Now, which are the type of, the strong bases? When we say about strong bases, some example, we can say amide anions here. So, NH2 minus. This is the amide anion. So, this can be used as a sodium salt. Amide anion can be used as a sodium salt, NaNH2. Sodium amide, it is called. Then another thing which we can use it is, say, potassium, say, tertiary butoxide here. So, potassium tertiary butoxide is a strong base again. No non-nucleophilic base, CO. Then potassium tertiary butoxide, tertiary butyl alcohol and potassium here. Okay. OH replaced by, H is replaced by potassium here. So, this is a potassium tertiary butoxide. So, when we are using it, it is better to use it along with a solvent, DMSO, dimethyl sulfoxide. It is used as a solvent. Why? Because DMSO, it is a polar aprotic solvent. Okay. So, the anionic base, it is not well solvated, thus increasing the basicity. Because we want strong bases here for removal of the 2 moles of HX. So, we need a strong base. So, therefore, when we are using this potassium tertiary butoxide as the base here. Okay. So, it is used along with the solvent DMSO, because the solvent DMSO, it is a polar aprotic solvent. Correct. So, the anionic base, it is not well solvated. Therefore, the basicity increases. Correct. So, it will become a strong base, strong enough to remove 2 equivalents of HX. Because we have to remove 2 equivalents of HX here. That is why we want a strong base there. So, let us illustrate how the reaction proceeds. Briefly, I will tell you from, say, geminal or vicinal dihalide, how the reactions are proceeding. Let us have a quick look at it. Say, we will take an example of a, say, vicinal dihalide. Let us see. So this is our, say, R, alkyl halide, H, then X will be there, another X, correct, H. So, this is our vicinal dihalide here. So, it is reacting with a strong base, say NH2 minus here. This is NH2 minus, strong base. So, this proton, it is getting removed here. Okay, this is attacking this proton here. Then this CH bond electron pair is used, it is forming the pi bond here. Okay, then this X is getting removed here. This is the first step. That is the E2 mechanism here. It will be followed, following the E2 mechanism. E2 mechanism. This is the step 1 here. Okay, so it will be in this mechanism, only 1 mole of the HX will be eliminated. Okay, so we will be getting a intermediate. What is the nature of the intermediate here? A vinyl double bond. So this is the thing we are getting here. That is a vinyl intermediate, vinyl halide intermediate we are getting here. So this vinyl halide intermediate, it will be further reacting with the amide anion here. This is the amide anion. So this will be reacting, this will be taking this proton here. Okay, then this CH bond electron pair, it will come here. Then this X will leave. So we will be getting again, this again a E2 mechanism, and we will be eliminating 1 more mole of HX here. Okay, so the product will be R, C, triple bond C, R. This is the alkane. We get the alkane here. This is how the alkanes are synthesized. This is the mechanism here. Okay, so the vinyl halide intermediate, this intermediate is known as vinyl halide. Vinyl halide intermediate is formed here. Now the problem here, why we need strong base, I will just discuss later, because the vinyl halide, eliminating the HX from vinyl halide, it is not an easy job. That is the reason we want a strong base here. Correct. Now, this is in the case of, say, vicinal dihalide. Vicinal dihalide. Now, in the case of a geminal dihalide, so what will be the type of mechanism? So, in the case of a geminal dihalide, it is the same, more or less same kind of a thing only. So, RCH, then we have, say, C, we have seen X, another X here, that is why it is geminal. Okay, here what happens, the NH2, this is our strong base here, NH2 minus here, so this will be taking this proton here, correct. Then this CH bond electron pair, it is used to form the double bond here. Okay, then this halide, it will go. So this again, it will be following E2 mechanism, removal of 1 mole of HX here, and we will be getting an intermediate, again as in the case of the vicinal dihalide, we will be getting a vinyl halide intermediate here. Okay, like this, it is a vinyl halide intermediate, correct. So this vinyl halide intermediate, again it will be reacting here. Okay, and NH2 say minus, NH2 minus, this proton will be taken here, then this electron pair here. So this is the mechanism here. Okay, the reaction will proceed in this fashion. Again, this will be an E2 mechanism. E2 mechanism. Then we will be getting a alkene here. Okay, that is R, C, triple bond C, R. An alkene will be produced. So one more HX is removed here, minus HX. That is 2 moles of HX are removed, and each step it follows the E2 mechanism. Okay, so this is how the alkynes are synthesized here. So simple examples we can, we can give any number of examples here, alkyne synthesis, but say a simple reaction we can say visualize. Say if you want, I can just give an example here. Say pH is C6H5. That is then we can say CH2. Then we can say chlorine. Again say C6H5. So if this compound, it is treated with say 2 equivalents of NaNH2 minus. Okay, that is, it will be 2 equivalents. What will be the product formed here? 2 equivalents are needed. So we'll be getting say C6H5, then C, a triple bond here, then C6H5. Correct? So this is the alkane being formed. That means 2 new pi bonds are formed here. That's the important point. 2 new pi bonds are being formed here. So excess quantity. The strong base is needed first thing, and we need excess quantity here. When excess quantity is used, we get this kind of the elimination. That is consecutive eliminations. 2 eliminations will take place, and we get an alkyne synthesis. Okay. Now, why we need a strong base? I will just briefly tell you. The strong base, because removal of the second equivalent of the HX from the intermediate vinyl halide, RCH. So the vinyl halide, intermediate vinyl halide we have seen here, RCH say double bond, say CRX. So this is intermediate vinyl halide here. So the removal of the second HX, mole of HX, it becomes difficult here because this carbon atom here, it is sp2 hybridized carbon. Important point here. In the case of the vinyl halide here, that is the carbon atom here, that is H and X, are both bonded to sp2 hybridized carbon atoms here. Okay, these bonds, sp2 means it will be a short bond and it will be a strong bond. Okay, compared to sp3 hybridized carbon atom, that means the CH bond, that is we have the CH bond and the CX bond. Okay, these are all these are all what you call sp2 hybridized carbon atoms here. Bonds are shorter bonds, stronger bonds than sp3 hybridized CH and CX bonds there. Okay, of an alkyl halide. Therefore, a strong base is needed to remove the HX here. 2 moles of HX here. So the relative strength of the CH bond, how it will depends upon the hybridization. The relative strength of the CH bond depends upon the hybridization. We have seen that. So sp hybridized bond, it will be the stronger compared to sp2 than it is compared to sp3. So this is the order of the strength of the bond here, bond strength we can say. Therefore, that is the reason for removal of the second mole of HX from the vinyl halide intermediate, we need a strong base. So thank you very much for listening.